Okay, what questions you guys have this morning? Yeah. Okay, who remembers what the mean value theorem says? So it's about the secant line and the derivative being equal. Slope of the secant line anyway. Yeah. Yep, at least one point on the curve has the same derivative as the average slope from the two endpoints of the interval. So if f of x is blank and say on AB and blank on AB, then there exists C in AB with f prime at C equal to f of B minus f of A over B minus A. What goes in the blanks? Yep, continuous and differentiable. Okay. So you have to be continuous on the entire closed interval. You have endpoints, you can't really be differentiable. You can be one directional differentiable, but you can't be two directional differentiable at the endpoints. So you have to be differentiable on the interior, continuous with the endpoints, and then you can find a place on the interior where the derivative at that point is equal to the average change, average rate of change over the interval. Okay. What's the interval that we should probably be looking at here? Zero, 3. It actually tells us to look at 0, 3, right? Okay. So we need to be continuous. And differentiable. Okay. So how am I going to make this thing continuous? Where's the first place that it might not be continuous? Yeah. At 0, right? I've got a change from function 1 to function 2 in this piecewise function from 5 to minus x squared plus x plus a at 0. Right? So we want to be continuous at 0. So what it has to be true for it to be continuous at 0? Yeah, the limit as I approach from the left and the right has to be 5. There's no limit from the left, so just from the right, it has to be 5. So as I get close to 0 with this quadratic, I need this quadratic to start getting closer and closer to 5. What a value gets me closer and closer to 5 when x gets closer and closer to 0? A equals 5. Yeah. So we're going to set a equal to 5 to make that limit from the right equal 5. That'll give us continuity at 0. Okay. How am I going to get continuity at 3? Sorry, no. I have continuity at 3. Where's the other place that I need continuity? I need continuity at 1, right? So what value do we have to match at 1? Yeah, at 1, this isn't like standard notation, but I'm going to call it f of 1 minus. That's going to be the inside function, because that's the one that's to the left of 1. That's going to be equal to, if I put 1 in there, I get a is 5, plus 1 is 6, minus 1 is 5. And then f at 1 from just a little bit above, that's going to be m plus b. So I know that m plus b has to be equal to 5. So far, so good? Sorry? On this one? If you put 1 in here for x, you get minus 1 squared plus 1 plus 5. 1 squared is 1, minus 1 is minus 1, plus 1 is 0. Okay. How do I get, so I've got continuity as long as I set m plus b equal to 5. How do I figure out differentiability? I can't really do anything. I've got 2 variables there. So we can't really do much more with the continuity, but we also have to have differentiability. Where do we have to worry about differentiability? Yep. Everybody hear that? Maybe not. So on the left, I've got a parabola, right, that's upside down. I don't know what it looks like, but it looks like this, sort of, right? Let's say we look like that, and this is at 1, because that's where we have differentiability issues. Okay, continuity says that we actually filled in the hole. So if I can make it continuous, I fill in the hole. And then on the right, I have a line. For it to be differentiable, that's not going to work because I get a corner. That's not going to work because I get a corner. What I need is I need to continue in the exact same direction as I was going before. Not with a curve, but with a straight line. Right? Okay, so what I want is I want the derivative here to equal the derivative here. Does that make sense? Okay. The derivative here is m, because that's the derivative of the straight line. The derivative here is minus 2x plus 1 at x equals 1, which is equal to minus 1. Good? Okay, so we need m equal to minus 1 for differentiability. So far, so good? Okay, so I have a, I have m. What else can I fill in now? B. A equals 5. M equals minus 1. B equals 5 minus m, so that's going to be 6. So far, so good? Anybody have questions on that? other questions you guys have on this section or otherwise?
Can you do 23?
20. Sure. We're gonna do 23. She called out first, but then we'll do 4. So we're given an initial acceleration. Sorry, we're given an acceleration, just A, an initial velocity and initial position, and we want to find the body's position at a time t. So I need to do some sort of undo differentiation. Think about what derivative gives me this function. So if A, acceleration is negative 49 sine of 7t, we got to figure out, okay, what function could I derive to get A? And that's going to be my velocity function. I want the derivative of this to be equal to that, right? Okay, so what's this function going to kind of look like? What function do I take the derivative of and get a sine? I'm going to start with a cosine function. And if I think about how the chain rule works, what's supposed to go inside the cosine function here? 7t. Okay, if I take the derivative of the cosine of 7t, what do I end up with? If I take the derivative of that, I get 7 with a minus sign, sine 7t. That's not quite good enough, right? Because I want minus 49. Yeah? Okay. So what do I have to do to make this minus 49 instead of minus 7? Multiply it by 7. Yeah. So we're going to set v equal to 7 times this cosine of 7t. And we always get to add on a constant, right? Because if I take the derivative of a constant, it just disappears. Okay. So this is what v is going to be. Questions on how we got v? Okay. We are told that v at 0 is equal to 7. So let's plug in and see what c is going to be. Because if I know what v of 0 is, I can figure out what c is. That gets rid of 2 variables, right? So that's 7 times the cosine of 7 times 0 plus c. Cosine of 0 is equal to 1. 7 equals 7 plus c. Tells me c equals 0. Good? Okay, so we know for sure the velocity function is equal to 7 cosine of 7t. The position function, we have to do this again. So s of t should be some function whose derivative gives me 7 cosine 7t. Who can tell me what that's going to be? Sure. Yeah, if I put sine of 7t in, the derivative of the sine is the cosine, and then I get the chain rule, which multiplies it by 7, so I get 7 cosine 7t, but I have to add a constant, right? Because we don't know what that constant was before it disappeared. Okay, and we're told that s of 0 is equal to minus 6. So s of 0 equals minus 6 says that sine of 7 times 0 plus c equals minus 6. Sine of 0 is 0, so -6 equals c. Tells me s of t is equal to sine 7t plus -6, or just sine of 7t minus 6. Where do we have questions on that one? Yeah. No, not a double integral. It is repeated integration with a double integral. What you're doing is integration over two different variables. Does that makes any sense? Okay. Just a quick picture. Integration defines the area under that. If I get like a 3D graph and I have some surface, if I sort of integrate over that square, this is some region R, and this surface, that's F, that would be a double integral. The first integral is with respect to x, the second integral is with respect to y. Yeah, this is repeated integration, but not a double integral. Yeah. You could maybe turn it into a double integral, but it'd be sort of weird, tricky, and just doing it to do it. Yeah. Okay, other questions on 23? Okay, you said number 4? Okay, so we've got f of x equals square root x minus 7. We're on the integral 7 to 14. Okay, we should first check, is this thing continuous on the interval from 7 to 14? It's a square root function. It's defined everywhere on the interval. Square root functions, where they're defined, are going to be continuous. So yeah, it's continuous. Is it differentiable on the interior of the interval? Yeah. If we were at 7, it would not be differentiable, but differentiable on the boundary points not happening is okay. I just need to be continuous on the boundary points, right? So this is differentiable on 7 to 14, but not at 7, right? F prime at 7 doesn't exist. And that's okay. We don't need it to exist for the mean value theorem. It just has to be differentiable on the interior. How do I know that F prime at 7 does not exist? Yeah. I can take the square root of 0, but then I can't put it in the denominator. Right. If I look at the derivative of this is x minus 7. This is x minus 7 to the 1/2, right? So this is x minus 7 to minus 1/2, and then I have to multiply by 1/2. That minus puts it in the denominator. If I put 0 on the denominator, things break down, right? Not defined at x equals 7. Okay, but that's okay. We don't need it to be defined at x equals 7. All right, so I want f of b minus f of a over b minus a equal to f prime at c, for some c. We need to find c. If I put 14 in, I get the square root of 7. And if I put minus f of a in, that's 0. And this is 14 minus 7. So this is the square root of 7 over 7. This is 1 over the square root of 7. Good. And so we want 1 over 2 x minus 7, the 1/2 equal to 1 over the square root of 7. How do I solve that? I guess, why is that what I want first? Here? Write 7 as the square root of 7 times the square root of 7 and then cancel them? Yeah. No matter what, it's just an exponent rule. Okay. Other questions before we ask, why is this the thing that we want? Okay, so why is this what we want? This is the derivative. We want to set the derivative equal to the slope of the secant line. Figure out where that happens. So to figure out where that happens, we solve for x in this equation after we set them equal to each other. What do we do to solve this? Cross multiply. So you get a square root of 7 over 2 equals the square root of x minus 7. Square both sides. 7/4 equals x minus 7. X equals 7 plus 7/4, which is 35/4. 28/4 plus another 7 is, 35/4. Questions on that? Other questions you guys want to talk about today? Okay, 4.3, we've already kind of talked about when we were talking about optimization. We just didn't formally call it first derivative test or anything. So let's sort of formally talk about 4.3 stuff. So to do that, we need a corollary of the mean value theorem, which is kind of obvious, but the corollary. Is that the first time you guys have seen this word? Have I used this word before? No. Okay. So theorem, corollary, lemma, proposition. These are all true statements that we've been able to prove or that you can prove in math, okay? These are true statements. Okay, so it's a theorem, not a theory. A theory is a science thing, which everybody thinks is true, but you can't actually prove a theory, right? You can have very, very strong supporting evidence, but you can't actually prove it. In math, we actually get to prove things. Like, under these assumptions, these things are definitely true. There's no doubt about it. It will always hold. Okay. The biggest ones, these are the theorems. These are big idea statements. Okay. Corollaries are applications or things that result from the theorem. Very, very short proofs. If you know that the theorem is true, then the corollary is true with just a line or two of reasoning. Okay. These follow closely from theorems. Special cases, quick applications, etc. Okay, lemmas on the other hand, so for corollaries, the theorem happens and then the corollary happens. Lemmas are sort of the building blocks for the theorem. They're the things that you prove, little pieces that help you piece together the proof of the theorem. And then propositions, they're kind of standalone things, anywhere between like a lemma and a theorem. They're not real big ideas, but they're not really used as building blocks, that sort of thing. They can still be like moderate ideas, small ideas. They could be a big idea, but typically if it's a big idea, you just call it a theorem instead of a proposition. Okay. So a corollary here is something that falls out from the mean value theorem immediately. And this corollary states, if f prime of x is less than 0 on AB, then f is decreasing on AB. And similarly, if f prime of x is bigger than 0 on AB, then f is increasing on AB. I haven't stated things perfectly precisely because I still have the same hypotheses as the mean value theorem. So probably what I want to do to state things perfectly precisely, but sorry, I can still do square brackets on the conclusion. I need round brackets on this corollary. And let's make the additional hypothesis f is continuous on AB and differentiable on AB. Those are our initial hypotheses for the mean value theorem. As long as those hold, then if f prime is less than 0 on that interior, then f is decreasing on the entire thing. If f prime is bigger than 0, then f is increasing on the entire thing. Okay, why would that be true? Just short proof, we can actually prove this pretty easily. We need to show, we'll do just A, because B is pretty much the same. We need to show if A is less than B, then f of B is less than f of A, right? That's what it means to be decreasing. If I go farther or right along my inputs, my outputs go down. That's a definition of a decreasing function. Okay. So, and this isn't just A and B, so maybe I should put in here, let's go x1, x2, x2, x1. And that should be for all x1 less than x2 less than or equal to A less than or equal to B, right? If I take any 2 points in the interval, I want that the function goes down between those 2 points. We'll look at x1, x2. The hypotheses for the mean value theorem hold on this interval, right? I'm interior to the original interval, so this is still going to hold for the mean value theorem. So there is f prime of C equal to f of x2 minus f of x1 over x2 minus x1. And f prime of C is less than 0. So f of x2 minus f of x1 over x and x2 minus x1, these two things have opposite signs. Right? This is negative. for this fraction to be negative, the numerator and the denominator have to have opposite signs, right? Okay. Therefore, if x2 minus x1 is bigger than 0, we have f of x2 minus f of x1 is less than 0, making f of x2 less than f of x1, which is what we needed to show. Quick corollary, there wasn't really big ideas. We just used the mean value theorem and saw that if you have a negative fraction, you have to have opposite signs on the top and the bottom. Not much of a big idea for the proof of the corollary. The mean value theorem had bigger ideas. Okay. So if we want where a function's increasing or decreasing, we can just look and see where is the derivative positive for increasing bits, where's the derivative negative for decreasing bits. And if the derivative is continuous, then it can't change from negative to positive without going through 0. So we can figure out where those intervals of increase and decrease are based on where the derivative is equal to 0. Okay. So let's just write that down. We find critical values. These are places. The derivative can switch signs. So f prime is 0. F prime undefined. Endpoints of domains. Those are where we can switch signs. Okay. And then break the domain into intervals based on these critical values. Assign a positive or negative derivative to each interval. Okay, there's kind of a lot there, so let's see an example. Okay, so let's look at this. What's the easiest way to do the differentiation with this one? Logarithmic differentiation. Okay, so I get that y prime over y equals over x minus 2 plus 1 over x plus 4 minus 1 over x plus 1 minus 1 over x minus 3. And if I multiply everything by y, we end up with the x minus 2 and the x minus 2 cancel in the first term. We good with that? So I'm going to write this down here. I get a x plus 4 over x plus 1, x minus 3, plus the x plus 4 here and here cancel. So I get an x minus 2 over x plus 1, x minus 3. Okay. Plus, I have x minus 2, x plus 4. And I'll get a minus sign on it because of that minus sign. And then I get an extra x plus 1 in the denominator. And the same thing here. Only the extra in the denominator is on the x minus 3. So far, so good? Okay. I almost have a common denominator, right? Okay. The common denominator is x plus 1 squared, x minus 3 squared. On the first term, I need both of them. Here, I need both of them still. Let me write that an easier way then. And then on this term, I need an x minus 3. And on this term, I need an x plus 1. Maybe the quotient rule was easier, but this is easier algebra than what I was thinking maybe. But in my head, it's easier. Okay, this is 2x plus 2. Gonna FOIL that out, x squared plus 2x minus 3 minus, let's go with an x minus 3, x squared plus 2x minus 8, x plus 1, x squared. Oh, I could have done the same thing here, couldn't I? Let's do that. That'll make our lives easier in a second. Okay. Got 1 minute. Let's boil this out real quick. 2x cubed. How many x squareds do I have? I've got 2 of them and 4 of them, so I've got 6x squareds, and x minus 6 of them and plus 4 of them is minus 2, and then a minus 6. And I've got a minus. I've got a 2x cubed. How many x squareds? I've got minus 2 plus 4, so that's plus 2x squareds. How many x's? Minus 16, minus 4, minus 20 x's, and then plus 16. And x plus 1 squared, x minus 3 squared. Those cancel. I have 4x squared, minus 2 plus 18x, and minus 22, or x plus 1 squared, x minus 3 squared. I don't see how that factors right away, but we'll continue this guy tomorrow.